So this video is going to focus specifically on doing some calculations having to do with specific heat, but I'm going to start with a little discussion of specific heat. So specific heat of a substance, again, is unique to that substance. So this is intrinsically part of that substance. So water is the big one. It's the one that we do a lot of different experiments with. It has a specific heat of 4.18. Or again, the definition of your calorie is for every 1 gram of pure water, it goes up 1 degree Celsius. But we have ice. Ice has a different specific heat. But then what we were talking about before, the ethylene glycol has a lower specific heat than the water. So that's going to be something to notice. And then we have some metals down here. Okay, they have lower specific heats even than that. So water is quite unique in that it has a high specific heat. So the bigger the number, okay, so the bigger the value, the more heat it will absorb without changing temperature. Okay, so water it's very influential on our planet, excuse me. Water can absorb a huge amount of heat. So if you think of Lake Michigan in the summertime is usually pretty cool until you get to the end of the summer. That's because it takes a long time for that heat energy to store up in there, and so that the water temperature gets comfortable enough to go swimming in there. So that is why they talk about, like, closer to the lake, sometimes the temperature of the air is different because of that big body of water. So water is one of the higher specific heats that we have. There are probably other substances out there that have higher ones, but please notice it compared to other things, it is highest. So we're going to use specific heat, and we're going to use this very famous equation. Q is equal to mc delta T. So Q is equal to M is mass, C is specific heat, delta T is the change. So you could write this underneath it. So heat is equal to mass times specific heat times the change in temperature. So we are going to be using joules or calories for our Q. So I'm going to put calories underneath it. Mass is going to be in grams. Our C is our specific heat, is joules per gram degree Celsius, or calories per gram degree Celsius. And our delta T is going to be in degrees Celsius. So how much does the temperature change? So we can calculate how much heat. So we're going to be calculating heat by how much mass we have of the substance times how well does it absorb the heat, that's its specific heat, and how much does the temperature change? How much does the temperature change? So delta T is going to be final minus initial temperature. And you're just going to subtract. So delta means change. So delta always means change when we see it in science in general, specifically also in chemistry. So how much does the temperature change when I do an experiment? So I'm going to work a couple problems so you could see how this very important equation is used going forward. So pause the video so you could write down this problem because I'm not going to pause too much here. So I have 25 grams of water has a specific heat of 4.18 joules per gram degree Celsius. And again, the specific heat will be given to you. When this water is heated, the temperature changes from 22 degrees Celsius to 45 degrees Celsius. How much heat was absorbed by the water? So again, I have 3 things that I need. Okay, I need mass, I need specific heat, and I need temperature to change, okay, in order to calculate my heat. Okay, so I'm going to be using Q as my heat. My mass is 25 grams. So you'll like this because there's no moles or anything we have to worry about. My specific heat is given as 4.18 joules per gram degree Celsius. And then what is my change in temperature? Well, final temperature is 45 minus 22 degrees Celsius, minus 40. So the change there is about 23 degrees Celsius, 23 degrees Celsius. So what do my units come out to be? Well, this is grams, and grams is on the bottom here. So grams cancels grams. And then my degrees Celsius cancels degrees Celsius. So I'm left with joules. Okay, so I'm left with joules. So heat could be calculated in joules or calories, depending upon the specific heat that you're given. So when you multiply this all out, you get around 2403.5 joules. So 2,403.5. Let's talk about sig figs. So I have 3 sig figs pretty much. I do not go off the specific heat when I do my calculation. So I have 3 sig figs. And sometimes you're going to see it convert to what we call kilojoules. So kilojoules, 1 kilojoule is equal to 1,000 joules. So what I'm doing is moving the decimal 3 over to the left. So I get about 2.40 kilojoules as my final answer with 3 sig figs. So again, you're going to see a lot of units of kilojoules going forward. All right, so let's try another one. So again, pause the video and see if you can do this one on your own. So this is 15 grams of a metal is heated and the temperature changes from 22 to 96 degrees Celsius. If the heat gain was 2,400 joules, what is the specific heat of this metal? So you're just changing what variable is unknown. So please pause the video now and see if you could try this one on your own. So you were given the heat this time, you were given the mass, and you were given the change in temperature. So you had to find your C, your specific heat. So joules is going to be over here. You're going to bring the grams over. You're going to bring the degrees Celsius over here when you do the division. And so you're going to end up with 2.2 joules per gram degrees Celsius is your specific heat. And that should make sense, okay, in terms of the units. Okay, if you get a specific heat higher than 4, which is the specific heat of water, you've done something wrong. Okay, so please note those numbers should make a little bit of sense when you are looking at them. So again, I'm just solving for a different unknown. So this last problem I'm going to work is I have 15 grams of a substance was heated and produced 440 joules of heat. The specific heat of the substance is 2.93 joules per gram degree Celsius. The initial temperature was 20 degrees Celsius. What is the final temperature? So this one, I'm going to kind of work with you because, again, there's a couple different ways you can do this type of problem because you're looking at the change in temperature, So let's set it up. I was given heat. Okay, that's in joules. So I'm going to put 440 joules over here on the left. That's Q is equal to MC delta T. I have 15 grams. I have my specific heat is 2.93 joules per gram degrees Celsius. And then I don't know my final temperature. So that's going to be X, and my initial temperature is 20 degrees Celsius. So with this calculation, again, you're going to have 440, and then when you multiply this out, this comes out to be, I'll do the math for you. 15 times 2.93 is about 43.95 times X minus 20. So I'm going to divide both sides by 43.95. So I end up with around 10, so 440 divided by 43.95 is about, about 10.01 is equal to X minus 20. So all I have to do is then add 20 to both sides, add 20 to both sides. So X is going to be around 30 degrees Celsius. Now this one is kind of tricky because I have only 2 sig figs because of the 440, but my number is 30 degrees Celsius. So 2 different ways you could write this number. You could put a 30 and then put a decimal after that. That means there's 2 sig figs. Or you could put 30 in a line over that. That's another notation that makes the zero what we call significant. So you could either put a decimal after it, or you could put a bar over it. So with these types of problems, you could also solve this whole part of the equation as X. And then what you could do is then when you get the X here, then you could just figure out, okay, am I adding or subtracting from that. And so again, the final temperature, because I'm heating it, the temperature is probably going to go up. So obviously, you know that the temperature is probably going to be greater than 20. You can make this your whole X in terms of your algebra if you wanted to do it that way, but the more correct way is to do it this